All right, let's get started. So it's a pleasure to welcome today's speaker. It's Susan Hermiller from University of Nebraska at Lincoln, and she's going to tell us something about subgroups of the group of dyadic piecewise linear homeomorphisms of the real line. Susan, please.
Okay, well, thank you very much for inviting me to speak in this seminar. It's really neat to be here and to see all of you. So as Elia just said, I'm going to be talking about subgroups of the group of dyadic piecewise linear homeomorphisms of the real line, not the interval necessarily. But I will be talking about Thompson's group F and dyadic piecewise linear homeomorphisms of the unit interval a bunch as well. Everything I'm going to talk about today is joint with Conchita Martinez-Perez. Okay, so I will start by talking about Thompson's group F and just introducing it for people who aren't very familiar with it, but also discussing a whole lot of things that are known about what groups can be some subgroups of Thompson's group F. In particular, a whole lot of results about the fact that a lot of things can't be subgroups of Thompson's group F. So I want to then move to talking about things like the automorphism group of F or the commensurator group of F and say, well, what can be subgroups there? But before I can do that, I need to talk a bit about how you would think about elements of F as actually homeomorphisms of the real line rather than the unit interval. And then talk about how people have set up nice ways of looking at finite index subgroups of the automorphism group and the commensurator group in as subgroups of the homeomorphisms of the real line. And then finally get to talking about results about who can be subgroups of those two groups. So that's the outline of the whole talk. But first, let me start with just setting up a bunch of notation. Okay, so homeo plus of R is the group of orientation preserving homeomorphisms of R. So if I think about a homeomorphism as a map from R to R, I can draw its graph. And if I draw its graph, it's a homeomorphism. So it's got to be basically always going up, or it's got to be always going down. And if always going up, it's orientation preserving, and if it's always going down, it's very not. So I want the ones going up. All right, so anytime I talk in this talk, I'm really always going to be thinking about homeomorphisms of either the real numbers or the unit interval, the interval from 0 to 1. So just let J be a subinterval of R, but I'm going to think it's either all of R or it's I. So piecewise linear homeomorphism, a homeomorphism built from pieces, is dyadic if every linear piece has slope a power of 2, and the breakpoints, the places, so again, if I start drawing the graph of this thing, it's going to have a linear bit, and then a steeper linear bit, and then a shallow linear bit, and so on. Every one of the places where the slope changes, I'll call those the x value, the first coordinate, the breakpoint there, all those breakpoints need to be in the dyadics, in the rational numbers where you're only allowed powers of 2 in the denominator. Okay, very bit of a mouthful of notation here. Oh, I should be doing things with my spotlighter here. So this notation is going to come up a lot, PL2 plus DC. So PL means piecewise linear, 2 means dyadic, plus goes back to this word orientation preserving. There's one other thing I want to just have for everything I want to look at today. Because I'm going to look at infinite domains, right, R instead of just a compact interval, I want to make sure that the breakpoint set is discrete and closed. I don't want to have a bunch of breakpoints getting closer and closer and closer to something. Okay, so mostly, as I said, I'm going to be looking at piecewise linear homeomorphisms of the reals, but at the start, to talk about Thompson's group F, I'll be looking at the example when J is the unit interval. And so there's a nice picture that I had from another talk, so I couldn't resist giving it to you instead of something hand-drawn. Okay, Thompson's group F is exactly the set of piecewise linear, dyadic, orientation preserving homeomorphisms of the unit interval. This DC now is just completely a red herring because we've got a unit interval. You can have only finitely many breakpoints anyway. It's finitely presented. It's cut two generators. You don't need to know who these two are. X naught's going to come back in an example later in the talk. So I thought I'd include the graphs of the two generators to give you a sense of what's going on with this group. Okay, so the theme of the whole talk is who can be a subgroup of everything I want to look at. So let's talk about F first. Who can be a subgroup? And in particular, lots of people can't. Sorry, lots of groups can't. So first of all, S is torsion free. That means any non-trivial finite group can't be a subgroup. But in particular, I just wrote Z mod NZ, right? You can't do Z mod NZ for n greater than or equal to 2 inside of there. There's a theorem of Cannon, Floyd, and Perry that says anytime a subgroup of F is not abelian, it has to contain an infinite rank free abelian group inside of it. It's just got to be huge if it's not abelian. Okay, so in particular, since the free group on two generators, by the way, I'm using free of 2 because F means Thompson's group F, so I don't want to repeat that there. So the free group on two generators can't contain an infinite rank free abelian subgroup, so he can't be a subgroup of F. If you're a finitely generated nilpotent group, but you're not abelian, then again, you can't contain an infinite rank free abelian subgroup because finitely generated nilpotent groups are polycyclic. They have finite Hirsch length. Can't be done. So any of those can't be a subgroup of F. In particular, a fairly standard example of such a group is the Heisenberg group. He can't be a subgroup of F. Okay, the next example of something that can't be inside of F, or can, involves restricted Riesz products. So anytime you've got a group G and a group H, you can build this thing called a restricted Riesz product, where you take a direct sum of copies of G. So this bracket H here is just meant to be a placeholder to say, well, if I write something like GH, I just mean G in the copy of little g who's in the copy of G corresponding to that element of capital H. So I have a direct sum of copies of G. H is going to act on that direct sum of copies of G to give me a semi-direct product. And the way H acts, the conjugation action, well, if I just act on GH, I conjugate GH, I get the same element G in capital G, but now it's going to be in a different copy of G. It's going to be in the copy of G corresponding to H prime H instead. Okay, so Dubin-Sapir basically souped up that Cannon-Floyd-Perry result. Remember, Cannon-Floyd-Perry said that if H is not abelian, and he's a subgroup of Thompson's group F, then he's got to contain an infinite direct sum of copies of Z. Well, Dubin-Sapir said, in fact, it's got to contain a little bit more. It's got to contain a Riesz product of Z with Z, which is just a direct sum of Z many copies of Z, semi-direct product with Z. Colin Blake came along and said, well, what about other, Z squared or something like that? What can you do? In fact, he proved a lot more than what I've got written on this slide here. He said that if G Riesz H is a subgroup of F, then H is either infinite cyclic or it's trivial. Those are the only options that you can put up on the top part of that. Okay, but I want to focus on this idea that you can have Z squared down below, but you can't put the Z squared up above in this dichotomy here. Okay, another example of something that you can't put inside of Thompson's group F is any Baumsag-Solitar group, BS1n, for when the absolute value of n is at least 2. And that follows from a result of Higman's that said an element of F can't have nth roots for infinitely many n. So just really quickly, I want to convince you that this guy does, because I'm going to use that again later. So this thing right here says, this relation right here, for example, says that A is equal to B, A to the n, B inverse, otherwise known as A conjugated by B to the n, or I guess conjugated by B inverse the way I've been doing things. So it's already got an nth root. But if I just start conjugating by B some more, if I do B minus J, for example, A B to the J, well, that's B to the minus J minus 1, A B to the J, B to the J minus 1. And there needed to be a B inverse in there. So that was B to the minus J minus 1, A to the n, B to the J minus 1. And if I just keep doing that over and over again, I end up with A to the n to the J. And if I do the same unraveling, I get A is equal to B to the J, A to the n to the J, B to the minus J, which is B to the J, A B to the minus J to the n to the J. And so A is a root for infinitely many different numbers n. Okay, I should have probably apologized for my atrocious handwriting with my stylus here. Just in case it is illegible, I've got the final result of what I just wrote printed on the page now. So BS1n can't be in there. Okay, but what I want to talk about today isn't so much F as much as his automorphism group, the automorphism group of F, and the Krentz-Rader group of F. All right, so if you remember from my outline, I said, in order to do this, in order to start talking about the automorphism group or the Krentz-Rader group, I need to somehow think of F as homeomorphisms of the whole real line and not just the unit interval. So this is a way that has been developed to do this, not by me. It goes back at least to Matt Brin. I'm not sure how far back further it might go than that. So the idea here is to build a piecewise linear function from the real line to the open unit interval, where the interval from 0 to 1 goes to the interval from 1/2 to 3/4. The interval from 0 to -1 goes to the interval from 1/2 to 1/4, and so on. So each of these intervals gets mapped down. This is the official, this is, in symbols, this is the picture that I think is definitely worth more than the symbols, at least for me, for seeing how this function works. Okay, so now if you do that, and then you do the function that does sigma, that goes to 0, 1, and you follow that with a function from Thompson's group F that I'll call little f. Well, any function in Thompson's group F has to map 0 to 0 and 1 to 1. And so it's got to map the open interval from 0 to 1 to the open interval from 0 to 1, and then follow that with sigma inverse. You get a dyadic piecewise linear homeomorphism from the unit interval to the unit interval. And in fact, it's got finitely many breakpoints because the original function f did. And so it's everything nice. And we get an injective homomorphism from F into our group of piecewise linear dyadic homeomorphisms of R. And I'm going to call the image of that, which is just homeomorphic to F, I'm going to call that F hat, but I'm really just going to think that's Thompson's group still. It's just Thompson's group in another guise. Okay, so what we've just done, actually, I should have pointed this out before I change this. So we've just done is we've said Thompson's group F is a subgroup of the set of all group homeomorphisms of R that are orientation preserving. So let's talk about who can be a subgroup of that. So the answer initially, in some senses, kind of completely determined by another piece of information. At least if you're talking about finitely generated subgroups, sorry, finitely generated subgroups. And I have to admit, I tend to believe that all groups are finitely generated, although I do have infinite rank abelian groups in this talk, so I admit to some two-facedness on that. Okay, but if you're a finitely generated group inside of the homeomorphism group, sorry, if you're a finitely generated group, you can embed inside of the homeomorphism group if and only if you're left orderable. Okay, so one thing that means, among other things, is that you're torsion-free, or you can prove that more directly from the definition of the homeomorphism group. So again, you can't have Z mod NZ anywhere. But otherwise, this contains huge amounts of stuff, including everything in our previous list that didn't exist in F. It's got the free group and two generators. It's got the Heisenberg group. In fact, it has every torsion-free finitely generated nilpotent group. Inside of it, it's got BS1n for all n greater than or equal to 2. It's and 1 for that matter, and 0. It's got Z re Z squared. It's got the whole gamut. Okay, so that gets us to the question of we've got this group that we started with on the very first slide of just the piecewise linear dyadic stuff. What about subgroups inside of here? How much does that restrict things? But I want to do a deeper dive. I want to talk about how you really kind of can say the automorphism group and the commensurator group are also sitting inside of the homeomorphism group. In fact, they're even inside of this piecewise linear dyadic subgroup. And then talk about who's the subgroup inside of those pieces. So that's the next couple of slides, is explaining how I'm going to somehow get these two guys and wedge index 2 subgroups of them, not quite them, but close, inside of this spectrum of groups. Okay, to do that, I need some definitions. So I'm going to start with a function. It didn't have to be piecewise linear. I could have also just said any homeomorphism, any orientation preserving homeomorphism of R. So to be a translation by M just means that I'm some line with slope 1. If I'm going to be one periodic, well, then I can, maybe I can do a little bounce or something, but I need to keep doing that bounce every interval. And I'm just going to look like I'm marching up with some nice pattern. If I'm Z periodic, well, that means I could be marching up instead of with slope 1, I could be marching up here with another slope. So I could be marching up with slope Q over P. So I could have something that looks like this. And it doesn't have to be a single bounce. That's just my way of writing something that looks nice fast. But the thing I really want to talk about, even more than having those properties, is eventually having these properties. So for example, suppose I want to draw something that is eventually a translation. Well, it means that down here off towards minus infinity, I have to be a slope 1 line. But then I can do all sorts of funky things for a while. I can do something steeper. Since I want to stay in piecewise linear things, I'll just keep drawing little bits. And then, I don't know, can do something steeper for a while. and then I can shoot off towards infinity that way and be a line of slope 1. These two lines do not have to line up, right? I'm just saying on towards minus infinity, I have to have the property. Towards plus infinity, I have to have the property. I can do the same thing to be eventually 1 periodic, z periodic, and so on. Okay, we're okay with the pictures. I haven't paused yet. Is everybody okay with this? Okay, all right. Okay, so Matt Bryn showed that in fact, when you do this translation, this change of f, and by putting a little hat on top, the functions that we get in as piecewise linear homeomorphisms of the real line are exactly the ones that are eventually a translation by an integer. So again, it doesn't have to be the same integer up top, up to plus infinity and to minus infinity. It could be different integers, but it's eventually translation by an integer in both directions. And so, and as I said before, but I want to emphasize again here, these guys have finitely many breakpoints. Okay, so now how does this connect to the automorphism group of Thompson's group F? Well, another thing that Bryn showed is that in fact, the automorphism group of F is isomorphic to the normalizer of F inside of this bigger group it lives inside, right? This group of all the the piecewise linear dyadic homeomorphisms. Except that, note, I haven't actually put a plus sign here. I'm not assuming that these guys are orientation preserving. Okay, so in fact, if I want to define the map, if I do the normalizer from PL to DC, yep, oops, I'm making a hash of this. Let's get this better. PL to DC of R of F to the automorphism group of F. What am I going to do? Well, I take an element G and I'm going to map it to the function from F to F that just takes F and maps it to G inverse FG. So this is just, we're just basically saying the inner automorphism group inside of this bigger group, this piecewise linear group, that consists of inner automorphisms by things that map F to F, is exactly the automorphism group of F. Except that, of course, oops, thought I had changed that. It's really F hat, the copy of F that we've wedged in there. Okay, so I want to stick to looking at orientation preserving things, so I'm just going to intersect that with the homeomorphism group, the orientation preserving homeomorphisms. Matt Bryn also showed that that's got an extremely nice description. That's exactly the dyadic piecewise linear homeomorphisms of R that are eventually 1 periodic. I want to look at one more thing inside of here that's going to be a very useful group to consider later. And that's the ones that are both 1 periodic and map the integers to the integers. 1 periodic doesn't force that. It's possible that this 1 periodic thing is mapping every integer to an integer plus a half, for example. All right, so that's the automorphism group. The commensurator group, I'm going to give you less of the description of how to get there. Barrio, Cleary, and Rover showed that the commensurator group is in fact isomorphic to a commensurator group, a subgroup of piecewise linear dyadic homeomorphisms of the reals. Again, I will point out that there is no plus sign right there. I'm not doing anything orientation preserving now, but it's isomorphic to all the homeomorphisms that are eventually periodic. And again, I'm going to focus on the intersection of that with the orientation preserving ones. It's going to be an index to subgroup. So the eventually periodic and orientation preserving homeomorphisms. Okay, so here's the recap of everything I've just said. And here's where they live. F is isomorphic to Thompson's group F. The automorphism, excuse me, the automorphism group of F hat is isomorphic to the automorphism group of F, but then I'm putting a plus sign or even a plus sign followed by a Z on it. So this guy right here is just isomorphic to an index subgroup of the automorphism group. He lives inside of an index 2 subgroup of the commensurator group. He lives inside of the dyadic orientation preserving homeomorphisms of the reals, and they are all living inside of the homeomorphisms. Okay, so for the rest of the talk, what I want to talk about now is which groups can be embedded in these three groups up here. Who can live inside of those guys? Okay, so the next slide is going to take a while. It's a little intense. It is the table of everything. All in one go. So here goes. All right, so I will say first that everything in this first column here is what I had on like slide 3 of this talk. So we knew that the free group on 2 generators and the torsion-free nilpotent, violently generated nilpotent non-abelian groups none of them could live inside of Thompson's group F, so they can't live inside of F prime because it's isomorphic. And that came from Cannon-Floyd-Perry's argument about infinite rank abelian subgroups. We knew BS1N couldn't be inside of there because of Higman's theorem, and we knew that Z re Z squared couldn't be in there because of Collin-Blake's theorem. Okay, so that is that column. We also had this guy. And we knew that from, so by the way, this should be homeo, but I couldn't get this table to fit on the slide unless I shortened that. It really just means homeovar. So all of that followed from left orderability. We talked about that one already. So what I really want to focus on is what's going on in here. But I'll remind you that we know this subgroup structure. So as soon as, for example, you get a yes in one of these columns, you'll have a yes going off to the right forever after. And as soon as you get a no in one of these columns, you get a no going to the left forever after. So in some sense, I would say here are the results that are actually, at some sense, results, and the rest just follow from those guys. Okay, so this yes up here, sorry, can you see my, yes, okay. I guess I could do this too. This yes up here was actually, is actually a consequence also of Matt Brin's sequence down here. So I'm gonna focus on it down here instead. Okay, so Matt Brin showed there's actually a really nice sequence that you can build for the automorphism group of F, this index 2 subgroup of the automorphism group of F. The kernel is just F. The image is a product of 2 copies of Thompson's group T. And I'm about to use notation, abuse notation just horribly. PL2 plus DC at some sense of the circle. I only defined it for intervals, but these are the dyadic homeomorphisms of the circle. So building from that, and the fact that you can find a nice copy of the free group on 2 generators inside of T, using just doing a ping pong kind of argument, that means that this group has to map onto something that contains a free group and on two generators, and you can't do that unless you contain a free group on two generators yourself. Okay, so that takes care of these two guys also. So the rest of this talk now is going to be about the five guys that are left, the five results that are results that Conchita and Martinez and I we've got the preprint written. I'm hoping it's going to be on the archive in another few weeks, but you know, travel and other things may come into play, but soon. Okay, I will mention, on the other hand, that while it looks like there are five results here, for this torsion-free nilpotent non-abelian, we actually have three different proofs, one for each of these columns, using very different techniques. And so I'm actually going to admit that the different proofs that I'm going to talk about today, I'm going to talk about him. I'm going to talk a little bit about him at the same time. And I'm going to talk about the yeses, because it's a lot easier to show you something does embed. The proofs that things don't embed are a lot more complicated, and I, you know, have a limited amount of time, and there's only so much detail I'm actually ever willing to put into a proof. Maybe proof detail I'm willing to put into a talk, and I'll just admit that too. So those are the pieces parts that I intend to talk about. But I'm still on this slide and have this exact sequence up. These two proofs here both rely not just on this short exact sequence of Brin's, but it relies on several other short exact sequences built by Matt Brin and by Barrio, Cleary, and Rover to just sort of decompose these two automorphism groups, sorry, the automorphism group and the commensurator group, in order to get the arguments to work. Okay, so that is the plan. I'm going to get rid of those, get a little bit of this out of the way so you can see the check marks a little bit more again. I've got one little no slide, a couple of yes slides to go. Primarily, there are a few more results too, I'll admit, in here. Okay, before I go away from the big table, any questions, anything?
I guess I can ask, is there a column for the PL plus DC?
So I will admit I have not put all of the columns from the paper into this talk. So we don't have one that's just for PL. We have something that for what we call pseudo PL2 plus DC of R. And basically, this is built using tree pair diagrams rather than homeomorphisms in a very nice, concrete way. I will just very suggestively say the word transducer out there, since some people might be interested in that. That, you know, tree pair diagrams that you can build with those. So we do have another column, and it gets us more interesting things, but I didn't include it here. Anything else before I move away? Okay. All right, so this is the no slide first, the one that I wanted to talk about. So if you remember, this is in some sense just starting by repeating things that I said way back on slide 3. The way to prove that the free group on two generators and finally generated nilpotent, oops, that's definitely bad without writing non-abelian in there. The way to prove that free group on two generators and finally generated nilpotent non-abelian groups aren't contained in Thompson's group is to show that it's to show that subgroups of Thompson's group have to contain the infinite rank free abelian group, because the free group and these nilpotent non-abelian groups can't contain that infinite rank group. Okay, so that was a tongue twister. I'm not quite sure why. So for piecewise linear homeomorphisms with finitely many breakpoints, wanted to highlight a couple of results that have been known for a fair while. One from Ken and Floyd Perry basically said, if you are contained inside of Thompson's group F and you're non-abelian, then you contain this infinite rank free abelian group. But actually much earlier, Brin and Squire said, we're going to look at just piecewise linear homeomorphisms. We want them to be orientation preserving, and we want them to have finitely many breakpoints. But we don't care about the dyadic, all the rest of that. That's okay. They said, if you just have that and you take a subgroup inside of there that's not metabelian, then it's also going to contain this infinite rank free abelian group. Okay, so metabelian, just in case, we've got 1 is normal in N is normal in G, and N and G mod N are both abelian. And if your group has such a normal subgroup, then it's metabelian. Okay, so we want to look, though, at the automorphism group of F and the compensarator group of F, and both of those allowed infinitely many breakpoints. Discrete sets, but infinitely many in lots of elements. So what happens there? Okay, so what Conchita and I proved was that if you're a subgroup of the automorphism group of F with this extra restriction, so that, remember, the automorphism group of F was just the things that were eventually one periodic, that kind of marched up at slope 1 in some periodic way. And Z just said, well, let's just make sure when you're at an integer, you map to an integer at the same time. So anytime you're inside of that group, your subgroup of that group, and you're not metabelian, same as Brin and Squire, then again, you have to have a free abelian, free abelian infinite rank subgroup. So instantly we get this corollary that the free group of rank 2 can't be inside of this automorphism group. But all we've done is show something that's not quite what we were after, but we're hoping. Any of the nilpotent, finitely generated nilpotent subgroup of this guy has to be metabelian. In fact, I will just write this because it's not permanent. It's on the slides after all. We have an argument which we came up with last night, and so I don't want to claim we know it's true yet. We believe we have an argument that gets rid of the word meta, the prefix meta, and works for abelian as well. However, I've got this double star here because we actually do have a proof of this, because we have a proof of this without the Z. We're using our different proof methods. As I mentioned, we had proofs for all 3 of the columns for the finitely generated torsion-free nilpotent groups. So we actually can get rid of the metabelian in this part B, but with different techniques. It doesn't follow as a corollary of this one. Okay. Let's talk about a positive result. So here's BS1N. So BS1N is generated by 2 generators A and B. One relation, B inverse AB, is A to the N. And we claim that it actually does embed. This is one of the yeses in a table. It actually does embed in the commutator. Sorry, I always want to say commutator, commensurator of F. Okay, so what are the 2 functions, A and B? So here's A. So A, actually, before I draw A, here's just going to put the identity along here. A is just a line of slope 1 that's shifted 1 up from the identity. So what does A do to something? It kind of takes the whole plane and it moves it up along that identity line in some sense by 1. Okay, what's B going to look like? So here's B. B, whoops, go away. So for B, what I want to do is draw a slightly different line. Here he goes. So I want to draw a line with slope 1 over n. So remember n in absolute value, and I should admit here, we have this theorem for n, for positive n, for n greater than or equal to 2. Okay, so we've got this nice slope n, slope 1 over n line. What is B going to be? Well, if B actually is a power of 2, then the line with slope 1 over n, that is just B of t is 2 minus kt, he's already in the P, so I'll just emphasize this, PL2 plus dc of r, he's got the right kind of slope. Doesn't have any breakpoints, so definitely a discrete set. He's orientation preserving, he's everything nice, and in fact, the commutator, the commensurator, is exactly the things that are eventually periodic, but he's eventually periodic. This line is eventually a line all the time. Okay, so that's the nice case. But suppose we don't have n being a nice power of 2. Well, he's got to sit between 2 powers of 2. And so what I'm going to do is just build a function. So right here, I'm just going to build him between, so here's n and 0, 0, and 1. I'm just going to build a little 2-piece function that gets me from 0 to 0 to 1n. Sorry, n1. And then I'm just going to repeat him over and over and over and over, forever and ever, in both directions. Oops, wait, I should be doing that along that line. Oh dear, don't do that. Help. Okay. Let's see if I can get this to work. There he goes, down the line. Okay, so I've still got something that's periodic, so it's eventually periodic. And what I've built is something that satisfies exactly the relationship I need. I've got, if I look at b of a to the nt, well, that's b of a just adds 1. If I do a n times, I add n. I've got b of t plus n. But b of t plus n just means what I'm going to do is go across n. That's the same thing as going up 1. I've just made this periodic in that way. And that's the same thing as doing b of t and then adding 1, which is the same thing as a of b of t. Okay, so I've written QED. There's still a matter of proving that at this point, what I've really proved is that I've got a map from BS of 1n, not 2, into com of f hat. Plus, there's still the matter of proving it's injective, which I will happily throw under the rug because I want to move on to the next thing. All right, no screams. Okay, so I'm not yet really quite done with this BS1-2 thing because there's one thing I want to point out. So you might think from the fact that the commensurator group allowed BS12 to be inside that it's going to allow a lot of stuff. Maybe it's just huge. And the answer is rather not necessarily, well, it goes against that, what you might have just had for your intuition at least. So if you just soup this up ever so slightly, so this time I'm basically going to have 2 copies of BS1n inside of here. I'm going to have A and B1, where B1 conjugates A to the n, and A and B2, where B2 conjugates A to the n, and B1 and B2 commute. That can't embed. It's a very nice group, solvable, everything you could want, and it crashes and burns. So BS12 lives in there, but kind of only just is the takeaway I want to give with that one. Okay, so this is the last that of the proofs that I want to show you. This is embedding Z re Z squared inside of the automorphism group of F. Okay, so ignore A for a moment. I'll come back to him in a little bit. I want to talk about B and C here first. So here's B. So what B does is it does what X naught did. So let me remind you of who X naught was and where that lived and so on. So X naught was an element of Thompson's group F. So here is 0 and 1, 0 and 1. Thompson's group F map 0, 1 to 0, 1. And X naught was this black line up here, this guy right here, that maps the interval to the interval and sort of basically moves everything up the line a bit. What I'm going to do with B is I'm just going to say, well, B is going to be the guy that does that at every integer interval. So here's the identity line. And if I start drawing B, well, here he is in the first interval out to 1. And then there's going to be another copy of him out to 2. And there's going to be another copy of him out to -1, and another copy of him to -2, and a copy of him to 3, and so on. He's just going to keep doing that same bounce forever. Okay, C of t inside of this interval from 0 to 1 is going to be this thing right here, which looks like a mouthful. But if you analyze what's inside of here a little bit, I'm just going to kind of very carefully go around there. I've got X naught, X1 inverse, X naught inverse, X1. I've got a conjugate. This time I can actually say commutator. Excellent. I've got a commutator, and then I'm just conjugating it by X1 inverse. Okay, so in this picture up here, this guy is B, or X naught, on this interval. And also in this picture, this red guy is doing what C does. Outside of that interval, so I'm going to draw C down here too. It does this and then does a little hump. I know it doesn't look like that. That's not even a homeomorphism, but I don't know how to draw it visibly otherwise. But outside of that interval, C is just going to be the identity. So he's going to do that. Okay, so inside of this interval, I want to go back to this picture up here and talk a little bit more just about B and C. If I do take C and I conjugate him by B, what that's going to do, wrong way around, sorry. If I take C and I conjugate him by B, what that's going to do is it's just going to move C over a little bit. In fact, it is that little bump right there. It's the function that is that little bump, and otherwise is the identity on the whole interval. If, on the other hand, I conjugate the other way, if I conjugate C by B inverse, I get this purple guy along with the identity everywhere else. I get a whole bunch of if I take a look at all of the conjugates of C by B, I end up with a whole bunch of little one bump functions. They all just look like C, but the bump happens in different places along the interval. But they're in different places that don't overlap. And so that means that if I look at C to the B to the J and C to the B to the I, they commute. In fact, if I look at the group generated by the set of all the C to the B to the J's, I'm going to end up with a direct sum of copies of Z. And so if I take a look at, I've gotten way too much written on here. If I take a look at just the subgroup generated by B and C, what that group looks like, it's a copy of Z re C, where this C is generated by B. And this Z is really a direct sum of copies of Z. And there they are over here. Okay, so that's a copy of Z re Z. I'm trying to get to Z re Z squared, so I need a bit more. And unfortunately, I did not have the presence of mind to give myself a second blank slide. So I am going to start erasing some things, if that's okay. No screens. All right. All right. So get rid of all of this. Myself a little bit of room. I'm going to put A into this mix. Need to draw him. So I need another color. Yeah, blue. Here's A up here. The graph of A. Suppose I took a look at the subgroup generated by A and B. Well, what does A do? A basically says, let's move up one. B says, if I move up one, my picture doesn't change at all. And so, I mean, that's in some sense a very loose way of saying A and B commute. These two guys are just going to generate Z squared. So then there's still the question of, what about the group generated by A and C? And that's going to get me to basically saying, I'm going to, well, how do I say this? Yeah, okay. I think at this point, I'm just going to get to saying the thing I need to say, which is that A, B, and C really and truly and genuinely give me Z re Z squared. And I will leave it at that. So the Z squared is being generated by A and B, and the C is just, I mean, the Z is generated by C, but of course that really corresponds to a direct sum of Z squared's many copies of Z. And I'll have one of those for every element of the Z squared generated by A and B. So they will just be the conjugates of C to the A to the I, B to the J. Those are going to generate the different Z's in the great big direct sum. Okay, and
Could I ask a question?
Yeah, sure.
So I'm getting from that construction that maybe there's not enough room to do Z with Z cubed or something.
You're anticipating the first line of the next slide.
Oh, okay.
Nice question. Anything else before I move on? Okay, so my next slide is also my last slide. Running out of time here. So I think this question of what wreath products can embed in who is still very much interesting and open. And in particular, exactly the question that you just asked, Murray, does Z re Z cubed get in there? It's really not clear. It doesn't. You're right. That picture from the previous page didn't leave wiggle room. And so some new idea really is needed in order to get Z re Z cubed in there. And so I'll also just sort of remind you of that theorem of Cullen Blake's that I quoted initially. If G wreath H embeds in F, then the H had to be infinite cyclic or else trivial. The question is, even more general than this question of Z re Z cubed. Is it possible that if you embed in, for example, the automorphism group, that the top group here can be at most a subgroup of Z squared and nothing else? Anyhow, so there's also the question of who can go into bigger groups. So for example, this entire big piecewise linear subgroup, or the commensurator group, and so on. Okay, so that's one open question I wanted to, or rather set of open questions I wanted to point out. Here's another one. The automorphism group of F is finitely presented. So is the automorphism group of the subgroup where the maps eventually map integers to integers. So that follows from the exact sequences that Matt Bryn proved. So this is a result of Matt Bryn's, because both of these are built basically from, we have short exact sequences using F and T, and they're known to be finitely presented. But in fact, Barrio, Cleary, and Rover have also produced a very nice finite presentation for the automorphism group of F, for this index 2 subgroup of M. But as soon as you're finitely presented, or at least finitely generated, that leads to some computational questions. And I just thought I'd put one out there. So the automorphism group of F that maps eventually Z to Z is known to be autostackable. It's got a rewriting system of a very nice form. It's got it's a bounded regular, what are the adjectives? Bounded regular convergent prefix rewriting system. That's the one. Okay, so it's autostackable. We know that the automorphism group of F, this index 2 subgroup, also has solvable word problem, again from the same short exact sequences that we had before. But we don't know what algorithms apply. How nice can these be? How not nice can they be? What can their Dane functions look like? There's a lot of interesting questions out there to be had, I think, on the computational side of this as well. Okay, and that's it. I'm done. So thanks very much for listening.
All right. Thank you very much, Susan. Thank you. Okay. So now, if there are any questions that have not been asked yet, so you're welcome to ask them. So you can unmute yourselves and ask them, or ask them in chat if you like. Okay, so if not, let us thank Susan again. Thank you. So I'll stop the recording.